Okay, good morning everybody. This is Mr. Steele. This is actually Mr. Steele from Saturday, so I'm sort of time traveling right now. Happy Halloween, October 31st. Of course I am not here. I am at Challenge Day right now. So unfortunately that left me in kind of a conundrum because I wasn't going to be able to actually teach you this lesson, putting us irrevocably behind in our schedule. Well, fortunately for me, I have all the technology necessary to produce a video like this and teach you the entire lesson without the need of actually technically being in the room. It's kind of a metaphysically confusing idea, but in fact let's not think about that. Let's instead just start about thinking about math. And in particular we're going to start with tackling the idea of complex numbers, of which you probably don't know much about if you've never taken Algebra 2 before. And where we're going to begin, though, is going to be with a short little introduction that starts with where we kind of left off on Friday. So with the idea of graphing parabolas. So this will be like part 1 of our notes, is an introduction to the concept. Okay, so our introduction, as I said, we're going to start by graphing a parabola, and we're going to graph it in vertex form. So here's going to be kind of our start. And you can begin taking notes here if you want to. For the most part, this is just going to be kind of motivation for what we're going to actually be tackling today. So we're going to graph. And we're going to graph the equation, quadratic equation, x minus 1 squared plus 1. So it's a parabola, and of course it's not just any parabola, it's a parabola in vertex form. So, vertex form. What's nice about vertex form, as we talked about in class, was that it gives you the most important piece of information about a parabola for free, because you get the vertex just from looking at it. So to actually find that point, like that x comma y, that will be our central spot for the parabola, we actually just have to look at the one parenthesis sitting here. First, what makes x minus 1 equal to 0, because that will give us our x-coordinate. In this case, very clearly you can see that the value is going to be 1. So we're going to have our x value of our vertex be at 1. And of course, if this whole thing is equal to 0, the corresponding y value will just be the constant thrown on at the end. It'll be 1. So our vertex in this problem is going to be at 1, 1. So I can already go over and, as best I can, try to plot a dot. So there is my vertex. And of course, from the vertex we get some cool information. Before we even do that, though, obviously, our a value is going to be positive 1. There's nothing sitting in front of it, so we can tell it's positive 1, meaning that we're going to have a very happy parabola. Well, not very happy, just a generally happy parabola, nothing special in particular. But from our vertex, then, we can also get to very important piece of information as well. The axis of symmetry, which is going to be x equals the x-coordinate. So that's going to be a vertical line right here. So I will attempt to draw my axis of symmetry, staying on the line as much as possible with this little electronic pen. And then secondly, we also get the minimum value. And the minimum value of this parabola is just the y value of the vertex, which is 1. So our minimum value occurs right there. So those two pieces of information come pretty nicely. Other things that we can get, well, obviously we can find the y-intercept. That's always good. It's always good to get some of these pieces without really thinking. So for our y-intercept, we just plug in x equals 0. So 0 minus 1 squared plus 1 is going to be equal to negative 1 squared plus 1, which equals 1 plus 1, or 2. So my y-intercept is going to be at 0, 2. So I can once again go plot it over on the graph. Again, it's not easy to draw points, oddly enough, down here. There's my point. And now we also get something really nice, is because of the symmetry offered by parabolas, we also get a point over here. So the same relationship, just on the opposite side of the axis of symmetry. So I'm going to go change pen color and plot that down, since symmetry lets us have a third point. Let's go graph a point. There is my third point. So that came directly from symmetry. So, as far as the rest, the only piece of information we haven't found is the zeros, or the x-intercept. And so let's just go ahead and tackle those. Hopefully those will give us 2 more points. So zeros, let's see here. Well, let's see, zeros are when y equals 0. So, it'll be the same thing as the x-intercepts. So 0 is going to equal x minus 1 squared plus 1. Let's see, okay, you know what, that's just square root method. Let's just subtract 1 from both sides, make a 0, we'll get negative 1 equals x minus 1 squared. Of course, well, square root method, we have to take a square root at some point. So that's going to give us over here, we'll have plus or minus the square root, negative 1 equals x minus 1, and then just add 1 to both sides, and we're going to get that our zeros or x-intercepts will be at 1 plus or minus the square root of -1. So we just go over to our graph and we're going to plot that 0, those x-intercepts right there at 1 plus or minus the square root of whoa, hate to admit that I don't know something, but I don't know where 1 plus or minus the square root of -1 is. Well, let's think about this. We've got a happy parabola, so, like, you can imagine following my cursor, it's going to be something like that. Doesn't look like it's going to quite hit this line. Well, of course it's not. In fact, we know, from just looking at it, that there are no zeros. There's no x-intercepts for this equation because it never actually hits the line. Like, we could use a table to find 2 more points, and in fact, if you do use a table, well, I can show that. Let me just show that real quick. It's always good to illustrate the table part. Just switch to a blue pen. So for my little table, to get 2 more points, let's see, pick an x value that's close to the vertex. I'm going to choose, how about 3? So let's go up here to x equals 3. When I plug in 3, I'm going to have 3 minus 1 squared plus 1. That's 2 squared plus 1, or 4 plus 1, which last I checked equals 5. So we're going to have a point from the table at 3, 5. And of course, symmetry will give us another point. It'll be on same distance away from the axis of symmetry. The other point will be right here. So we also get a point at -1 with the y value 5 from symmetry. So that's cool. We get our 5 points, and we can actually go graph our parabola without any trouble. So finishing it off, it's not going to be the best parabola in the world. It's actually really hard to draw with this pen thingy. There we go. So there's my parabola. So the question you'd be left with is, okay, we graphed parabolas on Friday. Why are we wasting so much time talking about parabolas? Well, in fact, this whole setup wasn't actually a situation, or wasn't a problem for us to graph parabolas. It was really to talk about this whole issue right here. Because if you'll notice, we did all this work, and we were able to get some sort of expression for the x-intercepts, or the zeros, and yet, well, what does that expression even mean? Think about it for a second. 1 plus or minus the square root of -1. What would a calculator say if we tried to find the square root of -1? Gosh, if only I had a calculator sitting here. Oh, look at that. I have a calculator here. I'm kinda magic. So here's our calculator. So let's ask that calculator, what would happen if I put in 1 plus or minus the square root of -1? Or heck, what would even happen if I just put in the square root of -1? Well, let's check. So we're going to put this in the calculator. Calculator, what is the square root of -1? So we punch it in there, press enter. So I'm going to press enter. It's going to look like I'm erasing everything I just wrote, but that's not true. It's actually just entering. So the calculator says when I press enter, well, we've seen this before. Domain error. Domain error. It looks like it's an expression. There's some sense to it. Calculator says domain error. Well, so what does this even mean then? The calculator doesn't even know, but yet we could do math stuff with it, and we know there's like nothing here. Like, it can't possibly be anything real, because like if it was, it would actually touch the line. So the question is, what does this all mean? And that is in fact going to be the focus of our actual work today, is what does this whole idea mean? So that's where we're going next, is trying to find some meaning in this whole square root of -1 business. So let's move it forward a little bit. Okay, to get further into this idea and this mystery of the square root -1 business, let's look at the problem that really inspires kind of the entire idea. So it's a very simple seeming problem where we want to solve a quadratic equation. X squared plus 1 equals 0. So on its surface, the equation looks pretty simple. It's just x squared, it's got a number, it's equal to 0. We can use the square root method. So we go ahead and do it, following through like the good, intelligent people that we are. Make a 0 there, we get that x squared equals -1, and then using the square root method, we square root both sides, and get that x equals plus or minus the square root of -1. So once again, we can kind of see an answer. It feels like there's an answer here, but in fact, when we ask the calculator, all we get is domain error. And when we try to actually think about it, like it doesn't make any sense. Like, what does the square root of -1 even mean? It can't possibly be a real number. Well, in fact, it's not real. It's much like another object, or another thing that we've known about kind of all our lives, but that doesn't really exist. And that is, of course, the unicorn. Unicorn, it makes sense. It's comprised of pieces that we understand. So, for example, this part, well, that's a horse. Like, we understand horses. They're mammals. They run in Kentucky Derbies. And then right up here, that's also something we understand. That's a horn. Like the unicorn, though, like the components here, like horse and horn and flowing tail hair and mane and rainbow, like we understand all those pieces. But in fact, this entire thing, unicorn, like the unicorn, last time I checked, it doesn't exist. Like, there's no such thing as a unicorn. But yet we can kind of think about it. Like, the idea makes sense. Like, we can talk about it. We have things that we can do with unicorns. You know, we can put them in episodes of My Little Pony and such. Well, the same thing's true over here. Like, this thing, x equals plus or minus the square root of -1, it makes sense. Like, it's there. Like, it's got a plus or minus. Like, I see a square root, a negative sign. There's a 1. I know lots about 1. I have $1. Like, I know stuff like that. But the idea is, how can we, like, translate this? Like, this thing, we have a name. Like, we call it a unicorn. But what can we do with this? What we need to do is we need to transition our minds from living only in the real world, the boring old real world where there's no unicorns or square roots and -1s, into another place. And that place is, of course, Imagination Land. So in order to get to Imagination Land, let's actually just listen to the Imagination Land song for a second to kind of motivate us to go on the journey. So, here we go.
The Imagination song. Imagination.
Yep, we are traveling to Imagination Land. Yep, that's us in the little red balloon. We're going to make sense of unicorns and the square root of -1. I feel like we're almost there. Normally I'd sing the song, but let the professionals do their thing. Okay, here we go. We're ready to enter Imagination Land. I can feel it approaching. Here it is. Ha! We got it. We're here. We're in Imagination Land. Now we've got a value. The square root of -1, it has a name. It is I. And in fact, this can be our first kind of idea. We're going to call this square root of -1 thing. Well, it's not real. It's like a unicorn. I is an imaginary number. Like, we're going to just call it an imaginary number. Like, it is most definitely not real, but that's okay. Like, we just gave it a name. Just like horses with horns, which don't exist, are called unicorns. So here we go. An imaginary number. Well, you know, this is a really useful fact. Like, this is kind of our key fact here to remember. Square root of -1 equals I. But there's more that comes from it. So, like, let's remember one of our square root rules. Like, if you remember back at the beginning of last week, we talked about how the fact that square root of A times the square root of A equals A. Well, think about this. Square root of -1 times the square root of -1. Well, that's got to equal -1. So, in fact, if we I squared, if we square I, we actually get -1. And so, in fact, these two statements here, square root of -1 equals I, and I squared equals -1, are going to be the like mathematical fundamentals of our Imagination Land visit. Like, in fact, when I first started and first taught Algebra 2, I had my class actually chant out these things to try to get them in their head. Like, I would go, what is the square root of -1? They would go, I is the square root of -1. No, actually, that's wrong. That doesn't sound as rhythmic. I think it was, what is I? And they would go, I is the square root of -1, sir. And then I'd go, what is I squared? And they would go, I squared is the square root of -1, sir. And then we'd say that for a while and, like, make loud noises. And it was really entertaining for me, but it wasn't necessarily entertaining for them. I think it was kind of embarrassing for them, especially when, like, you know, someone would walk in with, like, a pass to the front office or something, and they'd be in the middle of chanting, I squared, sir. So instead, I won't make you do that. Instead, I'll just tell you, like, memorize this. Like, these are very important facts that we're going to use over and over again. Square root of -1, square root of -1 equals I, and I squared equals -1. Like, we just need to know those things. Okay, so before we start using them though, like what we're going to do is we're going to kind of try to come up with an idea of how to imagine what they are. Like where are these things? Like how do we even talk about numbers like I? Like what does that even mean? And to kind of help us there is I need a number line. So I'm going to go grab a number line really fast. Oops, that's not a number line. That's my Halloween costume. it, you can laugh for a second. Like think it. See. Do you get it? Maybe you don't get it. See, that's me, and that is a DVD player. So see, I'm not actually here, but I'm talking to you anyway, making jokes, and so DVD player. There's my yeah. Feel free. Okay, I'll pause for a second. I'll let you guys laugh. Laugh it away, like laugh at my Halloween costume. My joke. I made it funny. No, go ahead and keep laughing. It's okay. You can keep laughing. It's cool. Okay, fine. I guess we need an actual number line, so let's get one. Okay, and here is our actual number line. So the question we kind of ask ourselves is, where do we put I? Like, where does this imaginary number go? And so again, like it's not like it's a big concept for us right now, but I mean it's important to know. Like how does it relate to all these other numbers? Because like we can see numbers here. Like there's one goes right there. Like I can plot other kind of weirder numbers. Like 1/2, it's a rational number. Well, I know the way that goes. 1/2 goes right there. Like that's not hard. Square root of 5. Well, gee, that goes right here, somewhere between 2 and 3. It's not even difficult either. Negative pi. Well, that's not bad either. It's negative 3.14, so I could put that number right here if I wanted to. Well, the problem is, where does I go? Like, we can't just put I here. We can't just go I in that spot, because, well, that would be the spot for, like, 4.5. Like, I's not between 4 and 5. It's, like, it's not even real. So that can't be it. It's tempting to put I right here, but that's different. The square root of negative 1 is I, not negative 1. So that doesn't work either. So the question of where to put I actually comes down to the fact that I, being imaginary, not being real, actually has to go somewhere else. I isn't on the number line itself. It's above the number line. Like we can think of it as being like right here. Like that is I. And what's nice about that is it doesn't interfere with our real numbers, so it doesn't interfere with our counting. We don't now have to go like 0, 1, 2, I, 3. Like that doesn't work. What we can do is we can then say, okay, well, there would be 2i, be twice as high as I. We could go up even higher. We could go to like 3i, go 4i. If we went up high enough, we could go to 42i. Imagine that, an imaginary 42. And we could even go down the other way. Like we could do stuff like negative I, negative 2i, negative 3i. And so that's going to be kind of our concept. I goes off the line. I is something that's kind of above it. It's different than the real numbers. So now let's kind of formalize this even more. Okay, so our first real task with imaginary numbers is going to be to actually start plotting them and have a visual or geometric interpretation for them. Before we can do that, though, we need to kind of extend it, because imaginary numbers are kind of small. Like it's just kind of like this I thing. Like they only have I. Well, first we're going to provide a definition here that we're going to use a lot. We're going to talk about it in context. And so we're going to talk about another new kind of number. We're going to talk about a complex number. So what is a complex number? Because that was really the title of the lesson anyway. So a complex number is a number. Well, that's good. I mean, if a complex number is really an octopus, the question would be, why didn't we just call it a complex octopus? So that makes sense. A complex number is a number that looks like this, of the form a plus bi. And of course, a plus bi, where a and b are real numbers. So of course that makes sense. Complex number of the form a plus bi, where a and b are real numbers. So basically a and b themselves are real numbers, but because you have a real number and an imaginary number, basically any complex number has a real and imaginary part. So there's two parts to any complex number. In fact, that's basically how we're going to look at them, is in order to translate them and get some sort of visual, like we're going to use that idea of having both real and imaginary parts. So what we're going to do is, let's say this is our task. Like this will be our example. We'll plot a couple of numbers. So plot the following. Let's start with something that's not complex. Let's start with just a real number. Let's say we want to plot the number 4 on this grid. Well, right now we could do that without this changing this around, but what we're going to do is we're going to no longer just call this the xy plane, we're going to call this the xyi plane, where this side, the x-axis, corresponds to real numbers, or the real components, and yi corresponds to the imaginaries. So this is like the real axis, and then this is the imaginary axis, like two separate little pieces. So, if we want to plot a number like 4, basically 4 is really just, it doesn't have an imaginary part. It's just 4 plus 0i. So in fact, not even complex. Well, right here, 4, that's the real part. So we basically can go over here and plot it at 4 in the real and then 0 in the I. So there, right there, is 4. It's basically the same thing as the point 4, 0. In fact, that should make sense. I mean, look back at our last page. Like when we went through and looked at this, 4 was right here. So if we wanted to plot it, we would just put it right there on the point, right on the number line. Nothing bad there. Okay, so that's cool. But what if we want to actually plot a complex number? Like say 3 plus 2i. And you know what? I'm actually going to change the color here. Let's plot in a different color so it's a little clearer. Let's say we want to plot the number 3 plus 2i. So what we can do is we can go over here and basically say that, well, this is my real part. And of course, on our grid over there, we said the real axis was x, so that's going to be my x. Then over here, that 2, that's going to be my imaginary part. So I will plot that as my y. Basically, I'm going to turn this into the point 3, 2 in my head, and then go plot there. So 3 on the real plus 2i, there is going to be 3 plus 2i, basically represented by the point 3, 2. And what's interesting is, before I do a little more of this, like some calculators actually even handle this pretty well. Like they can use, they recognize this concept of having a complex number be represented as like a point. So like if I type into this calculator, the TI-86 that I used all through high school, 3 plus 2i, when you type that in there, you type in a complex number, it spits out the coordinate 3, 2. So in fact, this actually does make sense, even according to some calculators. So let's do like 2 more here. So for part C, let's plot the number -5i. So let's plot that one. So it's just imaginary, like you can tell that. Well, what we can do is in order to plot it, we can think of it as 0, we can think of it as 0 minus 5i. So the real part is 0, and the imaginary part is -5. So we just go plot it. So 0 here, it's nowhere on the side, 0 minus 5i. There is minus 5i. It's represented by the point 0, -5. Again, plotting it can be really fast. So let's do one more. Let's set this skill aside. So let's plot the number, how about, oh, that would be a C. That's not after C. How about -4 plus, I don't know, I. Well, let's say if we want to plot this, again, we can look at the real and imaginary. So the real part is -4. So over here I'm going to go -4. And then plus I, well, it's just plus 1i. So we can actually plot that one right there. There is -4 plus I. And so once again, we've been able to kind of translate these things and put them on the point. Kind of using that same idea we saw before, where the imaginaries are right here, there's the real numbers, now we've got a way to plot points, or we've got a way to plot complex numbers, and now we can kind of visually see where they are. They're kind of on the board, but off the line. So, from here, what else can we do with complex numbers? Okay, well now we've got kind of the visual idea, and plotting complex numbers will be a part of your homework and tests and everything, because it shows up on standardized testing all the time. But in fact, like, we want to be able to do more with complex numbers. Like, the whole reason of having them is to be able to help us solve equations. Like we saw before, that when we solved x squared, let's just write it in here. When we solved x squared plus 1 equal to 0, like we never really finished the problem, but what we got was we got x equals plus or minus the square root of -1. Well, now that we have a name for it, now that we can call this thing I, we can now say that, oh, well, x is just equal to plus or minus I. So really, the entire purpose of complex numbers and imaginary numbers, both the same, is to be able to solve equations that we couldn't solve before. So let's look at a similar equation here. So, another example. let's say we want to solve. So find the x values to make it true. X squared plus 9 equals 0. So I know in a lot of your heads you're tempted to factor, but in fact this thing doesn't factor the way you want it to. Like x squared plus doesn't fit the difference of squares idea. So instead what we're going to do is we're going to solve this and use imaginary numbers, complex numbers, to help us get a solution. So what we do is the same kind of thing as before. We're going to subtract 9 from both sides, and we're going to get x squared equals negative 9. Then, following through the square root method, we can square root both sides. It's going to give me x equals the square root of plus or minus the square root of negative 9. Well, remember, once we get stuff under a square root, in order to simplify it, we want to like jailbreak it. We want to break it into pieces and then find the pairs. So let's do that same kind of thing. So negative 9 is really negative 1 times 3 times 3. But here's kind of the interesting thing. Like, when we have negative 1 under a square root, we said that's equal to I. And in fact, I squared equals negative 1. Well, what if we wrote this like so? The square root of I squared times 3 times 3. That would be the same thing. I squared is negative 1 times 3 is negative 9, so we've got plus or minus the square root of negative 9. That works. Well, considering you're following through more on the jailbreaking, I squared is really just I times I. So this is really what we have underneath the square root. So when we go to jailbreak it and pull out pairs, we actually have two pairs to work with. We've got I times I, so an I is going to get out, and a 3 is going to get out. And remember, as the old story goes, one gets out, the other one gets shot and buried and covered up by the warden. So in fact now, for our final answer, we're going to get x equals plus or minus, and then the two things that came out, 3 and an I. So x equals plus or minus 3i. And now we have an answer to a question we didn't have before. Pretty nice, pretty savvy. Well, there's more. Like, it doesn't have to be limited to an equation like that. Like, basically, imaginary numbers are letting us now have answers for equations where before we'd have to say no real solution. Like, there's no solution to it. Or your calculator would have to say domain error. So at this point, you're actually smarter than that blue little calculator. So, next thing. Let's say we want to solve one little more complex one. Little more complex. Yeah, go ahead and laugh. It's okay. It takes me a little bit to write the problems on here. Okay, so let's solve. Oops. So let's say we want to solve this equation. 3 times x minus 4 squared plus 10 equals negative 26. So I want to find the x values to make it true. Well, let's do that. Let's do the normal process. So we'd subtract 10 from both sides, because I kind of see square root method happening here. What's that going to do? That's going to give me 3 times x minus 4 squared equals negative 36. And then again, in my goal to get that squared thing alone, I will divide both sides by 3. And that's going to give me x minus 4 squared equals negative 12. So from here, what do we do next? Well, we take the square root on both sides. It is the square root method after all. On the left, we can jailbreak out an x minus 4. On this side, we're going to get plus or minus the square root of negative 12. So once again, square root of a negative number. Okay, we're going to need I somehow. So let's break this up. So first, we can imagine this as negative 1 times 12, and then prime factor both of them. So I squared, as it says up here, is negative 1. Or sorry, negative 1 is, as it says up there, I squared. So we can write that negative as I times I, and then the 12 as 4 times 3, or 2 times 2 times 3. Once again then, we've got stuff to jailbreak out. We can jailbreak out an I and a 2, with the one getting shot, the other one escaping. That's going to give me now x minus 4 equals plus or minus 2i square root of 3. So realize that it's kind of interesting, or it should kind of make sense. Like the square root of 12 is 2 root 3. The square root of negative 12 is 2i root 3. Like in order to take care of that negative, we need an I. And finally, my last piece, I can add 4 to both sides. We're going to get as our answer x equals 4 plus or minus 2i root 3. And so once again, like none of these, I mean these answers that we've seen here, like every one of these problems has had an answer that isn't even real. Like it's just like a unicorn, it does not exist. But again, like because our math can kind of work, once we gave this a name and kind of built up the idea a little bit, we could actually find solutions to problems that otherwise we just have to go, no solution. Okay, so this is kind of the basic stuff. So what I'd like us to do is here, Now that you've seen a couple instances of it, I'm going to write up a couple try-it problems and then ask you to pause the video and then work through them, see if you can get the answers, and then check yourself after a couple seconds. So again, just so you can kind of get used to doing this before we move on from here. Okay, so our try-it problems. So here's our big opportunity to try it. So I want you to solve these two equations. And again, what you'll see is they're both going to be quadratic, so you should get two solutions. So there will be probably a plus or minus involved somewhere. So first, let's have you solve 2x squared equals negative 22. Should be kind of basic. And then number 2, let's have you solve x minus 3 squared plus 4 equals 0. So go ahead and please pause the video right here. Give a minute or two here to work through, see if you can get the answers, check with someone, and then once you're done, I'll come right back and explain the answers. So okay, go ahead and pause. Freeze! Okay, so I'm assuming that you already paused this, because otherwise this would be kind of awkward. So now I'm going to actually solve these guys. Or let me first give you the equation, or the answers. I'll do it in red, since we're kind of like correcting our stuff here. So for the first one, so what we got, 2x squared equals negative 22. What I'm going to do is I'm going to divide both sides by 2. That's going to give me a new equation, x squared equals negative 11. That's not a tilde, that's a negative. So from here, square root method, square root both sides, going to get x equals, that's a bad equal sign, x equals plus or minus the square root of negative 11. And what I hope you see is that this is really the square root of I squared times 11, or I times 11. And then of course jailbreak out an I. And of course then what we get is x equals plus or minus I square root of 11. So there's our answer to try it number 1. Okay, our second one. So again, using the square root method, so we're going to subtract 4 from both sides. So I'll do that in red down here. That's going to give me x minus 3 squared equals negative 4. Then I'll take the square root on both sides. Get x minus 3 equals plus or minus the square root of negative 4. And again, the square root of negative 4, think about what that is. That's negative 1 times 4, or I squared times 2 squared. So on the inside there, we've really got I times I and 2 times 2. There's the negative 1, there's the 4. Means I'm going to be able to bust out a 2 and an I with nothing left over underneath. So in fact, my equation reduces to x minus 3 equals plus or minus 2i, and adding 3 to both sides, doing it kind of in my head, but there it is, we will get 3 plus or minus 2i. So our second equation's answers were x equals 3 plus or minus 2i. So in fact, these answers are complete gibberish in the sense that if someone offers you 3 plus 2i dollars, they're pulling your leg. That's imaginary money. But in fact, like, we now have answers to questions that before we just kind of have to stop. So square root of negative 1 has a name now, we're playing with it. Okay, so what else can we do with complex numbers? Okay, now that we've kind of spent some time visualizing complex numbers, talking about like why we need them, and then actually using them to solve equations that we couldn't before, let's actually talk about some things we can do just with complex numbers. So it's going to be kind of contrived, but actually what we're going to do is we're just going to do some operations with complex numbers. We're going to treat them like other numbers, and do things like adding, subtracting, multiplying, dividing. We're going to do arithmetic with complex numbers. So to start off with, 3 of these skills are pretty straightforward. So let's start with the easiest of the 2. Let's start with adding and subtracting. So let's add and subtract complex numbers. Okay, well, basically, what I want us to kind of see and think about is what that actually would look like first. So if I'm going to add complex numbers together, like let's say, let me give myself some space here. So let's say we're going to add 7 minus 3i plus negative 2 minus 6i. So let's say we want to add those guys. Basically what you can kind of see is that each complex number has its own real part and its own imaginary part. So that's going to be kind of our motivation. We're just going to combine the real parts and then combine the imaginary parts into one complex number, and that will be our answer. So in fact, adding and subtracting complex numbers comes down to just combining like terms. That's really our only instruction that we need, is just combine like terms. So what does that look like? Well, I'm going to drop the parentheses because it's a plus, so that we can kind of see that it's 7 minus 3i plus negative 2 minus 6i. So looking at like terms, I've got a real part of 7 and a real part of negative 2. So 7 plus negative 2 is just 5. For the second part, for the imaginary part, I've got negative 3i and minus 6i. So in fact, negative 3i plus negative 6i is going to be just negative 9i. And so there is the sum of my two complex numbers. We get 5 minus 9i. So there's a single complex number that represents the sum of those two. So subtracting, not actually that much more difficult. Let's go with 1 plus 3i minus 2 minus 6i. Let's go with that. So the difference here is obviously that we've got this little minus sign. So the only thing we have to do before we combine like terms just like before is actually distribute in this minus sign. Like make sure we're subtracting both components of the complex number. So what we'll do to start is we'll kind of ghetto sprinkler in that minus sign so that our problem reads 1 plus 3i minus, well, minus 2, then minus a negative 6i, which is the same thing as plus 6i. So now we've got, basically as our answer, we've got real parts, 1 plus negative 2 is negative 1, and plus 3i plus 6i equals plus 9i. So our subtraction, again, very much just combining like terms, we just had to distribute in the minus sign first, so that we make sure that we subtract everything. So adding, subtracting is not difficult. So next let's move on to multiplying. Again, building up to the hardest one, which will be division. So first let's think about what the problem would actually look like. So if we're going to multiply complex numbers, we could have like, that's a really bad 5, isn't it? You'd make fun of me. 2 plus 5i times 3 minus 2i, whatever. There we go. So let's multiply these two complex numbers, 2 plus 5i and 3 minus 2i. Okay, so when you look at this problem, when you're multiplying complex numbers like this, the two parentheses are just sitting right next to each other, what you've kind of got to see or think about is a problem that you covered a lot, probably practiced a whole lot back in Algebra 1 or pre-algebra. And that was when you were asked to multiply stuff like x plus 4 times 2x minus 3. What you did was you had all these fun little things, like foiling in the box, and basically you just multiply all the little pieces together. And in fact, that's exactly what we're going to do. Like multiplying complex numbers is really the same thing as multiplying binomials. Like it's the exact same task. The only difference is at the end we're going to have to use some of our understanding of complex numbers to simplify this guy. So let's start by doing this, and I'll try to use different colors to try to make it clear. So first, 2 times 3 is, last I checked, 6. So that's our first little component. Second, so 2 times negative 2i is going to be negative 4i. So there's our first part. We've taken care of the stuff that needed that first 2. Next, so moving on to here, plus 5i times positive 3 is going to be plus 15i. And then last, but not least, we've got plus 5i times negative 2i, which is going to be negative 10i squared. So this kind of pattern, we won't always get the exact same numbers, obviously, when we multiply. We'll always have this kind of pattern. We'll have a number, we'll have some complex stuff in the middle, and then we'll have something with an I squared. So the question comes, what do we do from here? Because it seems like, okay, we did all this work, what are we doing? Well, first, there's one really obvious thing that we can do. We've got minus 4i plus 15i. Those are clearly like terms. So just like when we added and subtracted, let's just combine it into one imaginary piece. So we'll still have 6, then minus 4i plus 15i is plus 11i, and then we still got this minus 10i squared. So from here, a lot of students mistakenly just kind of call this a day and like stop here. But unfortunately, we have to think about this. Like 6 plus 11i, like that stuff looks okay. But this 10i squared, if only we had some interpretation of what I squared was. Like if only we knew a way to simplify that, like a fundamental fact of complex or imaginary numbers. Well, we do. I squared is negative 1. is I squared. I squared is negative 1. So as soon as we see that little guy, little I squared, let's just turn him into a negative 1. Because that will allow us to get rid of this I squared. Like, complex numbers don't have an I squared component. There's not some third little piece that we've been skipping. No, I squared is negative 1. So let's just plug it in. So 6 plus 11I minus 10 times what was I squared is now negative 1. So 6 plus 11I minus 10 times negative 1. And this guy can just be simplified. This really is the same thing as 6 plus 11I plus 10. And of course, once we get here, we again have like terms. We can just go through and say, okay, 6 plus 10 is 16, and then plus 11I. So the product of those two complex numbers, 2 plus 5i and 3 minus 2i, actually ends up being a fairly simple complex number, 16 plus 11i. So once again, just to kind of review these guys, like for adding and subtracting complex numbers, adding just comes up to be straight up combining like terms, combine the real parts, then combine the imaginary parts into a single complex number. When we go to subtract, the only difference is we first have to distribute in that minus sign, and then we just combine like terms, real and real, imaginary and imaginary. And then for multiplying complex numbers, all we do is multiply them the two of them as a binomials, since they really have two pieces each. And then from there we combine like terms, and we plug in that I squared equals negative 1, so that we can turn it all into just a real part and a complex part, or a real part and imaginary part. So from here, what I'd like to do is, before we move on, even though these are real basic skills, I'd like to have you do it once, just before we go on. So this will be our second stop for a try it for the day. So once I finish writing them out, if you can please pause the video for a couple moments, or a couple minutes, and let you work through, try to get these guys. Let's go with, for our first one, we'll do an adding one. Let's have you add 3 plus 5i plus negative 1 plus I. For our subtraction, let's go with 2 minus 7i minus 3 minus 6i. Then for our multiplying, let's go 1 minus 3i times negative 2 plus 4i. Okay, so I'd like you to go ahead, pause now, please, and then we'll go through all of these in just a second. And again, if you leave it on, it'll just be kind of awkward because I'll jump right to the answers, and you won't have actually moved forward in time or done anything yourself. So go forward, please. Okay, so let's actually go through these really quickly for you. So hopefully this is after a little bit of time passed, so that you've had a chance to actually try them. So I'm going to try to do them in as little work as possible, just for sake of time and for space. So for this first one, we're adding, so we're just going to combine like terms. So we've got 3 plus negative 1 is going to be positive 2, and then plus 5i plus I is going to be just plus 6i. So again, we don't have to factor out a 2, don't have to do any of that stuff, just leave it as is. Okay, for the second one, let's distribute in this minus sign. So we'll make this minus a positive 3, so minus 3, and then minus a negative 6i will be plus 6i. So then this basically turns into addition from that point on. So 2 plus negative 3 is going to be equal to negative 1, and negative 7 plus 6i is going to be equal to negative 1i, or just negative I. So our second answer is just negative 1 minus I. Okay, our third one. I'm not going to use different colors this time, so let's see. So 1 times negative 2 is negative 2. 1 times positive 4i will be just plus 4i. Negative 3i times negative 2 is going to be plus 6i. And negative 3i times positive 4i is going to be negative 12i squared. So from here, combine like terms and simplify. So in one step, we got negative 2 plus 10i, because 4i and 6i are like terms. Then remembering this is negative 12 times I squared, and I squared is negative 1. That means this whole expression down here is going to become negative 2 plus 10i, and then negative 12 times negative 1 is positive 12. And so then combining like terms, negative 2 plus 12 is going to be 10 plus our original imaginary part, 10i. So there are three answers: 2 plus 6i, negative 1 minus I, and 10 plus 10i. All fairly straightforward. So again, we've taken care of adding and subtracting and multiplying complex numbers just by using old skills like combining like terms and multiplying binomials. That leaves us just with division to tackle on our last slide, our last piece. Okay, you know what? I lied. Before we go on to the last thing, you've been dealing with a lot of talking and a lot of video lecturing here for a while. Let's watch a quick commercial instead. Let's just have a break for a second. It's a couple seconds. Haha, I bet you jumped. I love that one. Happy Halloween. Okay, so last task. So we've done adding, subtracting complex numbers. Now it's time to actually divide. So our last little piece here is going to be dividing complex numbers. Okay, so as part of dividing complex numbers, we're going to need to deal with this kind of idea of a complex conjugate. So before we go on, let's just define that so that we'll be able to use it and look at some of its properties, of course, first. So last definition, we've only had a couple. Basically, a plus bi, so a very general complex number, and a minus bi are called complex conjugates. So this is going to be our term, complex conjugates. So now what does that really mean? That means basically, in effect, they have the same real part. So notice they both have an a, just a normal positive a. So same real part, but opposite signed imaginary parts. So it's not really that difficult to identify. So if you've got the same real part, but then opposite signs on the second part, but otherwise the same, then you have complex conjugates. So for example, if I have 2 plus 7i, we can get that its conjugate would be the same real part, opposite imaginary part. And so we get 2 minus 7i. So 2 plus 7i and 2 minus 7i are complex conjugates. 1 minus 3i would have the conjugate 1 plus 3i. Again, visually, they're basically the exact same point. If you want to kind of see this, visually, they're the same point. So 1 minus 3i would be like right here. 1 plus 3i would be like right up here. They're the same point. They just have their imaginary parts are reflected across the real axis. Just one more, just kind of throw them out there. If we did like negative 4i, just because this does sometimes come up, its conjugate would have to have the same real part, so it'd still be nothing for the real part. Opposite imaginary part, so it'd just be 4i. So negative 4i and 4i are complex conjugates of each other, or conjugates. So of course, why does this really matter? Like, who even cares about conjugates? Well, here's kind of the cool thing about conjugates. Let me use a different color pen just to emphasize how cool this is. Complex conjugates, when you multiply them, something really cool happens. So let's just do this with the general ones first, kind of give it to you as a formula. So if I multiply a plus bi times its complex conjugate, a minus bi, watch what happens. A times a is a squared. A times negative bi is negative abi. Bi times positive a is plus abi. And then positive bi times negative bi is going to be negative b squared I squared. Okay, so there's it all multiplied out. Just like before, now let's simplify it. So what you can see is right here in the middle, negative abi plus abi is just going to go to 0. This entire middle part goes away. It's like it's gone. We've made a big 0 with them. So all we're left with is a squared minus b squared I squared. But what is I squared? Your mind should immediately be ready to call out negative 1. So a squared minus b squared I squared is really a squared minus b squared times negative 1. And negative b squared times negative 1 is just positive b squared. So the product of two complex conjugates is just a squared plus b squared. And in fact, a squared plus b squared, well, I mean, there's no I in our answer. Our answer is just going to be a real number. So in fact, once I figure out this mouse system, we actually just end up with a real number when we multiply a complex conjugate times its other conjugate. Like, when you multiply two of them, you get a real number. That's really cool. Not only do you get a real number, but it's really just the squares, the sum of the two squares of its real and imaginary components, or like the real part of each one. So, for example, like if I want to multiply 2 plus 7i times 2 minus 7i, what would I get? Well, we don't even have to really multiply this out if we don't want to. You could, of course, FOIL it if you wanted to, but all I do is I go, okay, first one is 2, so 2 squared plus 7 squared equals 4 plus 49 is 53. So the product of 2 plus 7i and 2 minus 7i is a real number, 53. Down here, 1 minus 3i, 1 plus 3i, 1 minus 3i, 1 plus 3i. Well, just square the two of them. 1 squared plus 3 squared is 1 plus 9, or 10. So notice each time when we multiply those numbers, we are getting a real number. And so that's actually really helpful, because let's say we want to divide two complex numbers. Let's start with a really easy one. We'll do 2, and then I'll let you try one. So let's say we want to divide 2 by 3 minus 5i. Like, let's say that's our division problem. We want to find an equivalent form. So in fact, that's exactly how our instructions are always going to read. Write an equivalent form. So that just means, like, how can we simplify this? How can we rewrite this so that it doesn't look so ugly? Well, what we want to think about first is, like, the reason we don't like this is I is equal to the square root of negative 1. So really what we have here is we have 2 over 3 minus 5 square root of negative 1. And remember, having square roots in the denominator was bad for old mathematicians because they only had an abacus. And abacusi? I don't actually know. Well, either way, those little bead dot thingies, like, they weren't as cool as calculators. Like, they could not divide by square roots. So in fact, the reason we have to change this and write a different form is really for the same reason as rationalizing. Like, we got to get rid of that square root in the denominator, even if we're giving it an imaginary name. So what we're going to do is we're going to look at it this way. So here's our problem, drawn a little bigger, still in blue because I've forgotten to change the pen color. What we want to do is we're going to multiply by something that will turn this bottom complex number into a real number. And what we're going to do is we're going to multiply by the complex conjugate. So multiply up and down by complex conjugate. And again, the reason is, as we just saw from those last couple examples in that little exploration on the left side of the screen over here, like, we know that when you multiply a complex number by its conjugate, you end up getting a real number. So if we multiply up and down by this complex conjugate, the denominator will no longer have an imaginary part. Okay, you'll just get a real one, and then the top will have the complex stuff. So, like, we'll be able to have our final answer with no square roots of negative 1 in the denominator anywhere. So that's what we're going to do, up and down by the complex conjugate. Let's get a different pen to do this. Okay, here we go. So up and down by the complex conjugate. So here I got a complex number down here. I'm going to multiply top and bottom by its conjugate. So the conjugate of 3 minus 5i is going to be 3 plus 5i. And I'll multiply it on top and bottom that way. 3 plus 5i. Okay, so now what's this going to be equal to? Well, actually the top is just as easy to simplify. This is 2 times 3 plus 5i. Well, 2 times 3 is 6. 2 times 5i is going to be plus 10i. So there's our numerator, 6 plus 10i. And it's okay to have an imaginary number on the top. That just means we have a complex number. On the bottom now, we have a trick for this. This is really the same as before. It's 3 squared plus 5 squared. 3 squared is 9. 5 squared is 25. We get that this is all over 34. So our answer is 6 plus 10i over 34. But what you might notice is that while this is an okay answer, this is good, this is the right thing, like, this isn't simplified as far as we could go, because, like, numbers can go, and there's a GCF between 6, 10, and 34. And in fact, that GCF is going to be 2. So what we can do is we can actually go through and like divide out the GCF for all those pieces. So like if we divide everything by 2 here, just to simplify, 6 divided by 2 is going to be 3, 10 divided by 2 is going to be 5, and 34 divided by 2 is going to be 17. So our bestest answer will be 3 plus 5i, all divided by 17. And there we have effectively divided two complex numbers. We've got our answer. And we could also write it this way, like if we were told to write it as a plus bi form, we could do 3 over 17 plus 5 over 17i. Like both answers are fine. I personally like this one just because it's a little easier to write, but both are fine. So let's do a second one just so we kind of hit all of them. Let's go with this one. 3 plus 2i, which we've used a bunch of times today, divided by 1 minus I. You know what, we really don't even, you won't even normally see the parentheses there when you go to do the problem, so let me erase it. Okay, 3 plus 2i over 1 minus I. So we want to divide these two, or as the directions will likely say, write these as an equivalent form. So we want to get rid of this I in the denominator. Okay, so we'll do the exact same strategy as before. Multiply up and down by the complex conjugate, just like it says here. Okay, what's that going to look like? Well, let's do this. First I'll put the parentheses in, because basically what's going to happen is we're going to end up multiplying binomials on top. So the complex conjugate of the denominator, what is it? I'm going to assume that you just said 1 plus I, because that would have the same real part, opposite imaginary, and then up and down by that same thing. So there we go. Now in this case, my denominator is actually easier to work with. Got 1 squared plus 1 squared is just equal to 2. So whatever comes out on top, it's going to all be over 2. So that's kind of nice. On top now, I can actually start working. So 3 times 1 is going to be 3. So we're just multiplying two complex numbers, which amounts to foiling. 3 times I is just plus 3i. 2i times 1 is going to be plus 2i. And positive 2i times positive I is going to be plus 2i squared. So there it is. There's kind of our multiplied out part all over 2 from our from multiplying out the complex conjugates. So now on top we just need to simplify. So 3i plus 2i is going to give me 5i. So I'll have 3 plus 5i plus 2, and then it's I squared, but remember I squared is equal to negative 1. So 2 times negative 1 all over 2. Then simplifying this one final step, we can write this as 3 minus 2 is 1 plus 5i all over 2. And notice this time there's no GCF for all the terms, like there's nothing that goes into both of those, so we can just call it a day. 1 plus 5i over 2, or if you insist on writing it out, I think our textbook does it this way, 1 plus 1/2 plus 5/2 I. Both are correct answers. And there we go. So we've now hit all 4 of the major operations of arithmetic for working with complex numbers. So we can now add and subtract by combining like terms, we can multiply by multiplying out binomials and foiling, and we can divide by multiplying up and down by the complex conjugate, which we found had this really cool property of turning complex numbers into real ones. So there we go. We've kind of hit on everything from the lesson. So what could possibly be left? Well, let's just have you do one final triad. So see if you can do all these operations. So what I'm going to do is, for this thing, I'm going to give you two complex numbers. So we're going to have 5 minus 2i, and we're going to have 1 plus 3i. So what I'd like you to do is 4 things. I want you to add them first. You know what, this would probably be easier if I just went through and actually wrote them out. So let's do that. So for skill, let's go 5 minus 2i plus 1 plus 3i. Okay, so first add them. Second, I would like you to subtract them. So 5 minus 2i minus 1 plus 3i. Third, please multiply them. So 5 minus 2i times 1 plus 3i, remembering about the I squared thing. And last but not least, I would like you to divide them. So write an equivalent form for 5 minus 2i over 1 plus 3i. Okay, so once again, just like before, if you can please pause and then work on these for a couple minutes, maybe 2 to 3 minutes, maybe a little longer, depending on it. Check with people around you, and then come on back. I will actually go through and explain these. So please do that now. Right now. Have you paused yet? Oh wait, if you did pause it, then at this point this is really awkward. Okay, so let's go to the answers. So let's do this really quickly. I know you've already kind of tried some of these, but you've done adding, subtracting, multiplying. Just throwing dividing in there too. So these first couple should have been pretty quick. So first, 5 plus 1 is 6. Negative 2i plus 3i is just positive 1i. So our first one is 6 plus I. Second one, so distributing that minus sign, I'll do it the quick way again. Minus, this becomes a minus also. We'll have 5 plus negative 1 is positive 4. And minus 2i minus 3i is minus 5i. So there we go. 4 minus 5i. So next one, doing the foiling. So 5 times 1 is going to be positive 5. 5 times 3i is plus 15i. Negative 2i times 1 is negative 2i. And negative 2i times 3i is negative 6i squared. So simplifying here, remembering that I squared is really the same thing as negative 1. That's hard to see. There. Okay, this will be 5 plus 13i, and then minus 6i squared, so plus 6, because that'll be negative 6 times negative 1. It's going to be equal to 11 plus 13i. And so there it is. Okay, lastly, dividing. So we're going to divide these two complex numbers. Going to do that by multiplying up and down by the conjugate. 1 minus 3i, 1 minus 3i. Okay, so I'll give myself some space here. So on the bottom, it's going to end up being 1 squared plus 3 squared, which is going to all be over 10. On top, I'm going to get 5 times 1 is 5. 5 times negative 3i is negative 15i. Negative 2i times 1 is negative 2i. And then negative 2i times negative 3i is going to be plus 6i squared. Okay, so what does that leave me with? That gives me 5 minus 17i. And then this is 6 times I squared. Well, that's just 6 times negative 1. So minus 6 all over 10. And of course, that simplifies to negative 1 minus 17i all over 10. And so there is our final answer. Negative 1 minus 17i all over 10, or if you prefer, negative 1 over 10 minus 17 over 10i. Both are fine. And so that pretty much does it for the lesson. Like, we've kind of looked through, kind of see all the stuff that we covered. Like, we started with just kind of coming up with a motivation for why we wanted complex numbers. Then we kind of talked about this idea of like where that square root of negative 1 came in, why it was a problem, and ways that we could kind of work through it just by kind of working like a unicorn, like making up this idea of a unicorn, a horse with a horn, saying that, okay, square root of negative 1 is this number I, which means I squared is negative 1. We kind of then worked on visualizing it, seeing where it was at, and that kind of figured out that it was on the board but above the line. From there we talked about how to actually plot it by extending that a little bit to 2 dimensions in this way, with a real and imaginary axis, and just plotting the real point and the imaginary point as like coordinates. Next we went on and we actually started solving with it, so we were able to use it as part of like the normal jailbreaking strategy. Since negative 1 equals I squared, let us pull out an I and get answers to problems we couldn't get before. Then we went on and started doing some operations with complex numbers. Specifically, like we added and subtracted them by combining like terms, and we multiplied them by just like foiling them out, multiplying binomials. Then lastly, I guess that's the same thing. That was because my video screwed up once. And then lastly, recently here, we went through and we actually divided complex numbers, talking about this idea of a complex conjugate, which is actually a pretty cool thing. That allows us to multiply 2 complex numbers and get a positive number, or get a number, well, it's always positive, and that of course let us go through and divide complex numbers and get answers that didn't have square roots of negative 1 in the denominator. Then we just practiced a bunch of times. So I think that's pretty much the end of the lesson today. For the remainder of the period, you can go ahead and work through and work on your homework if there's any time left, because I can't actually at this point tell you how long the video is, because I can't actually tell. So either way, I hope this has been beneficial. Hope you've been able to pick up a lot of the concepts and feel at least comfortable with it instead of just floundering day off with me at the challenge day. So anyway, happy Halloween, and this is Mr. Steele signing off. After, of course, a smiley face.